2017 multiple. Okay folks, second part of the 2017 multiple choice. Right, question 11. Essential oils are. This is just a KU point. Okay, so for a start, we know that they are oils, and if they're oils, then we are looking at non-water soluble. So get rid of these two, and then we're looking at volatility. Now, given that these are separated by distillation, volatile. Okay, that's it. Question 12, this is a straight definition again. Okay, so enthalpy of combustion of a hydrocarbon is the enthalpy change when. Okay, so combustion is when 1 mole of a substance is completely burned in oxygen. I have nothing else really to say about that one. The rest of them are not. This one's been thrown in to mess your kind of definitions in your head up with the enthalpy of neutralization. Enthalpy of neutralization is formation of 1 mole of water, so that's the sneaky one. This is a product one that's a bit odd to have taken up, and I suppose this at least mentions oxygen, but again, incorrect. Okay, which of the following is the strongest reducing agent? You'll notice I have pulled in the databook page for your reduction potentials. Okay, right, being very, very careful here. Okay, if it is a reducing agent, that means that it makes something else be reduced, which means it is oxidized. Okay, so we're looking for something which is running in this direction on the booklet, because these are the reduction potentials. So that helps you a little bit, because straight off I can get rid of fluorine and iodine, because if I find fluorine and if I find iodine, both of these are being reduced, they are not being oxidized. Okay, so they are not actually going to be giving away electrons for someone else to take, because they are taking electrons. Okay, so what I'm left with is it lithium or is it calcium? Now they are on the correct side, so they're going to oxidize, and then I'm just looking for which one is the highest up. Okay, because that's the one that's going to ping off its electrons as fast as it possibly can, and we have lithium. Okay. Oh, can't find, there we go. Couldn't find the mice working for a minute there. Okay, question 14. Right, we've got titanium chloride plus magnesium giving magnesium chloride and titanium. The atom economy for the production of titanium in the above equation is equal to. Okay, so atom economy, okay, is a percentage that we're looking for. And what we're looking for is the desired products over your reactants, all of your reactants. Okay, and we're just going to use masses. So our desired product is the titanium, so 47.9 divided by the mass of our reactants. So we've got our titanium chloride over here, so 189.9 plus I have magnesium, but be very careful here, there are 2 magnesiums, so I need to put 2 times my 24.3. And that's it, and make it a percentage. So I'm going to divide it by, times it by 100 or 100 over 1, depending on how you look at it. So correct answer there is B. Question 15. Vitamin C content of a carton of orange juice was determined by 4 students. Each student carried out the experiment 3 times. It's decent enough practice, okay. We've got a whole set of data. The most reproducible results were obtained by. So what we're looking for here is the narrowest range in the data. Okay, so if they'd managed to reproduce their experiment well, then each time they did it, they would have got exactly the same answer. So if the closer they are to having the same answer each time, the least variation in the results, you're going, that's the best one. Okay, so let's have a look. Your top and bottom range for student A is 2 centimeters cubed out. Our top and bottom range for student B, 26.4, 26.8. It's not bad, so that's only 0.4 out. And our student C is actually 26.9, 27, because that's another 26.9, so only 0.1 out. And then we've got 26.9 and 26.5. So most reproducible ones that we've got in there, definitely student C did the best. B student C. Okay, question 16. These are quite tricky. I actually wish I'd split this so it was a bit bigger, but hopefully you can still see it. Well, actually, you're probably looking at the actual paper as you're working with this anyway. Okay, so cyanohydrin compounds can be made from carbonyl compounds by reacting the carbonyl compound with hydrogen cyanide. Okay, and then they give you a little picture. Which carbonyl compound would react with hydrogen cyanide to form the following compound? So what we've got to do is we've got to go between this one here and this bit here to figure out where you needed to add this bit in, basically. Okay, so this one's got, on the top here, we've got an OH and the CN with an H off the bottom. So that tells me that this bit here, that C double bond O, is where I made the OH and the CN attach. And this hydrogen is this bit down here, because that's the extra bit of hydrogen. So what I want is a C double bond O here, and then I want my chain, this chain, attached on next to it. Okay, so you got to work this way back. Right, so here we go. So I'm looking for CH3, C double bond O, okay, and then I want my CH3, CH2, CH, CH3, CH3. That's what I'm looking for. Okay, and nicely, it's the top one. Okay, it's not the nicest question. You just got to be very careful about what you're doing. Okay, look very carefully at where the thing is you're looking for, which is this bit here. Okay, find it inside the thing that you've been given, and then work back. It's all just about replacing where things should be. It's a pretty common question to have. It's sometimes in the short answer where you have to draw out what you would need to have. This one, they're giving you options. Okay, question 17. Chemical reactions are in a state of dynamic equilibrium only when. Okay, so they've got a whole pile of things in here which are just wrong, and we're looking for the correct one. Okay, reaction involves no enthalpy change. Well, that's just not true. If I draw, here we go, here's our kind of normal reaction pathway. Okay, this would be the forward and that would be the back. Here is the enthalpy change. The enthalpy change is the same for the forward and the back, but it certainly involves an enthalpy change. Okay, so no. The concentrations of reactants and products are equal. Now, I'm not saying that's not possible in a dynamic equilibrium, but this is only when. So what you're likely to have is, here's my reactants at the top, falling down, ending up here-ish, you know, and here's my products at the bottom, starting at nothing, and then going flat as well, okay? It is possible that you could have a reaction where your reactants and products did end up at exactly 50%, you know, but it's not necessarily going to happen. In fact, that's very, very, very unusual. What will happen is that the rates will do this, okay? The rates will end up at the same point, because for everything that goes forward, you need something to come back. Okay, so that's correct. This one's wrong. Activation energies are equal is wrong as well. If we look at this one, again, the first diagram, there's the activation energy for your forward reaction. There's the activation energy for the back reaction. That's not going to change, and it's not equal. Okay, so D. Question 18. I think this was really gifted because he gave you all of the actual information, and I don't see why they wouldn't send you to the data book for this, but obviously they were saying it's 1 mark, so they're considering it a straightforward question. Okay, so really all we're looking for is, do you know where your positives and negatives go on? So I always go with, here we go, here's our normal reaction. Doesn't matter if it's exothermic or endothermic. I've drawn it exothermic here, but if I drew an endothermic, does the same deal. What's important is you break first and then you make. You break and then you make. Break must be plus and make must be minus. Okay, so let's do the break. The break here, they've even told you. They've told you which ones are broken, which ones are made, and they've put the multiplier in. Okay, so I'm going to break 1 hydrogen bond, well, a mole of hydrogen bonds, and I'm going to break a mole of bromine bonds, so 194, gives me a total of 630, and this is a positive. Okay, and then I make 2 sets of hydrogen to bromine bonds, so I'm going to do 2 times 366, which is 732, but that's actually a minus. Add these two together, my total is therefore minus 102 kilojoules per mole. There we go. Question 19, which of the following is a structural formula for glycerol? Well, glycerol is propan, so let's just get rid of that while I'm doing this. Propan 1, 2, 3, triol. You just need to know. Okay, so this one doesn't have an OH in it, forget that. Okay, this one is not an OH, forget that. And this one is, there you go. Last question of the multiple choice section. Which line in the table best describes the effect of adding a catalyst to the following reaction? Okay, the whole point of a catalyst is it gets you there faster, but it doesn't change where you're getting. Okay, so the position of the equilibrium is going to be unchanged. It's not going to shift. Okay, and what will happen to make that happen, in terms of getting there faster, is I speed up the forward and I speed up the back with exactly the same kind of hit. Okay, so forward reaction is going to increase, also the back will, but it's not even asking you about it. So there we go, last question of the multiple choice.